Now that we have developed the excitation tables, we're ready to come back and fill in our state transition table. We're ready to start with a D flip-flop. We're going to determine what the values for the D flip-flop need to be. We'll have two state equations. One state equation we'll have for flip-flop of Q0 in the next state and the flip-flop Q1 in the next state. In order to do that, like I just said, we need to solve, I decided to solve using D flip-flops. We added the two columns already, one for the D flip-flop input and one for the D0 flip-flop input. And then we'll use the excitation table to decide what Q next is. Right. This is the completed table, but I'd rather walk through how this was completed with you. So let me bring up the spreadsheet here. Right. Right. So here's the two columns that we're added. We need to determine what the input values are to our D flip-flops. And these are the easiest to use simply because our characteristic equation is Q next is equal to D, or D is Q next. Right, so if I say this as D is Q next, well then the input to D1 must be the same as the input to Q1. So Q1 in the next state is a 0. That means the input to our flip-flop D1 must also be a 0. Q1 in the next state here is 0, so this must be a 0. So all I'm doing really for the D flip-flop is once we know Q1 plus, Q0 plus, is we know exactly what our inputs need to be for the D flip-flop. Right. If you remember the characteristic equation, the excitation table gives you the same results. So this needs to be a 0, this needs to be a 1, 1, 1, 0, 0. So the input to the D flip-flop here, D1 matches the Q1 in the next state. Similarly, Q0 in the next state will drive the input to the D0 flip-flop, which will match this exactly. So 0, 1, 0, 0, 1, 0, 0, 1. So the inputs to the D flip-flop D0 will be the same as Q0 in the next state. All right, let's save that work. And that's where this table then comes from. Yeah. This is the same as what we just determined. This shows Q1 plus, fills in this. We take Q0 here to fill in this column. Now we want to determine the state equations for D1 and then D0. What we do is we take the column D1. So I just hid some columns in the spreadsheet. We look at our column D1. So the input to the D flip-flop is actually an output of our table here. We want to decide what the equation is that drives the input to D1. So think of D1 in this case as an output. Your inputs are the present state, Q1, Q0, and X. Right, so we can write this there as, let's see where we have the ones in this equation. We have the ones for the binary combination of 0, 1, 1, so 3, 4, and 5. So we say that D1 is a function of the inputs Q1, Q0, and X is the sum of 3, 4, and 5. So the summation symbol tells us where the ones are in our truth table. So if we were to map that out, here's the 3, here's the 4, here's the 5. We get this group of 2 then forms the term of Q1 is a 1 here, and with Q0 is a 0 here, so Q0 naught. That's this term. This term then, well, Q1's a 0, so we get Q1 naught. Q0 and X are both 1s, so Q0 X. So this ends up then being, this is the same up here, right? This is our equation then that we want to use to drive the input to the D flip-flop. Similarly, we do the same for D0. So D0, we pull it out of the table. It is now our output. Our inputs to the circuit are Q1, Q0, present state, and our input X. All right, so D0 is a function of these three inputs is equal to the sum of 1, 4, and 7. So here's a 1 at at 1, here's a 1 at 4, and here's a 1 at 7. So put that into a K-map, we have this group here, right, which turns out to be Q0 naught and with X naught, and that is OR then with this term that is Q1, Q0, and X. And that's our equation then for D0 that will drive the input to that flip-flop. Let's just go ahead and map this much before we talk about Z. Right? Because by now, you probably wonder what this looks like. What I'm going to do is I'm going to bring up Quartus. We're going to start drawing the circuit so we can have an idea of exactly what it looks like and how it will operate. All right, so I've got a blank Quartus project here. I want to insert a D flip-flop. I'm going to use the symbol tool. And I'm going to type DFF, right, which goes to storage and gives me a D flip-flop. I actually need 2 of them, and so I should have turned on insert mode. Let me grab another one here. We need 2, right, for Q0, Q1. All right, now let me make this a little bigger. And you should be following along right now as well, drawing this circuit. Okay, these D flip-flops in this library, right? This triangle is our clock input. Here's our input to D. Here's our output Q. These also have a preset. So PRN is a preset, meaning if you wire preset signal to that, whenever you assert the preset signal, your output of Q will be a 1. CLRN clears it, it's a reset. So if you were going to assert the reset signal, your output would be a 0. We'll actually just not wire that at this point. Let's just concentrate on D0, D1. Right. We will need inputs to this circuit as well, and a clock. Well, I'm going to name this clock. We'll have D0 and D1. We're going to have outputs from the circuit. Right? We're going to have Q0, Q1, Q0, Q1. All right, I'm going to wire Q0 to this flip-flop, Q1 to this flip-flop. Similarly, actually I want to wire the clock to both of these. Sorry, we don't have these as inputs. We're going to derive these inputs. The only input we have here is X, because my morning caffeine has not kicked in yet. So this circuit, right, only has 2 external inputs: the clock that drives the flip-flops and X. Let's go back now to the equation that we developed here. Right. Oh, sorry, slides here. Right. My equation for D0 is Q0 knotted and with X naught. Q0 knotted and with X naught. So this will be Q0. I'll need a NOT gate. Right. I'll need 2 NOT gates. I'm going to have an X naught. Somewhere I'm going to have a Q0 naught. I'm just going to flip this. And I'm going to wire up this signal here. Actually, maybe I'll just flip it back. And That's not what I wanted, is it? Oh, I haven't wired one of these in a while. Bear with me. All right, so if we do this, all right, I will now label this. This is Q0 not. And this will be X naught. All right, we said then that I need to AND Q0 naught with X naught. I need a 2-input AND gate here. And I'm going to need to clean this up a bit. We're just going to name the CLK for clock. I can wire these in like this. We won't have all these wires to look at. Shorten that up a bit. All right, CLK. All right, that makes that clock connection from that input pin to these by naming the wire the same thing. All right, I said now I want to drive D. I'm going to need another AND gate. Yeah, probably. And I'm going to need an OR gate. Right, so I said one equation that, right, this is X naught. X naught, and that's ANDed with Q0 naught. Q0 naught. All right. And then my other equation, I need a 3-input AND gate. Caffeine definitely hasn't kicked in. Q1 ANDed with Q0, ANDed with X. All right. Let's get our 3-input AND gate. We got X. Right. Q0. And Q1. That is what drives our flip-flop D0. Right? Our equation for this was our state equation for D0. This will be my flip-flop D0, right? The output of this flip-flop is Q0. I could put a little text note over here that says here. Actually, I could name this wire. If we wanted to, we could give this a name and say that this is D0 to make that a little more clear. Right? That's what our circuit looks like. Right? We're getting output from this flip-flop and output from this flip-flop. It's being wired back into here. This is why we call this a sequential circuit, and we say that the next state is based on the present state, right? It's influenced here by Q1 and with Q0. This portion is influenced by Q0 naught. So this is how your circuit's influenced by the present state. It's also influenced by the input, right, of x and x naught. All right, similarly, let's wire up Q1. So our state equation for Q1 or for D1, right, the input to D1 now needs to be Q1 ANDed with Q0 naught. Let's insert some symbols here. I'm going to need 1, 3 input AND gate. The 2 input AND gate. I'm going to need an OR gate for here. And we need Q1 naught. Another NOT gate here. Maybe I'll just give that just a little bit more room from the other. Right. Let's do that to generate Q1 naught. Q1 naught. This is going to be our input, D1. I just said that was Q1 ANDed with Q0 naught. Q1. Q0 naught. And I believe we have Q1 naught. Slide that out, make it a little more readable. And with Q0 and X, double check Q0 and X. All right, hopefully you're following along and drawing this. When you get done, you should implement this on a board and test it. Okay, there's Q0. Okay. And then I'll put in Q1 naught, Q1 naught. All right, bring these down a little bit. All right, so our external inputs to this circuit are input X and the clock. All right, these inputs D0 and D1 were determined by these gates. These gates are the result of the inputs X and the present state of Q1 and Q0. Right, let's save that. We can call it D. Sequence 110 DFF for my D flip-flop solution. All right, let's see if we can go ahead and run the analysis and synthesis here. Oh, I did not make that the top level. I know better. Yep, and I mistyped the signal name. Yes, that's D. That should be D1. Oh, and I just love it when Quartus lays down a NOT gate and gives it the same instance number. So logic function of type NOT and instance INST is already defined. So it used INST for this flip-flop. Then it used it for what? Logic function of type NOT and instance INST is already defined as a signal name for. Where did it use INST? Here. That says INST too. Oh, sometimes I just love Quartus. Let's make this INST 0. See if it likes that any better. All right. All right. So that is what our circuit would look like. A little bit different now that in terms of we haven't done something like this before, right? Where we combine a sequential circuit with a combinational circuit. Right? All right, we'll stop this recording here, and then we'll see how to implement actually the JK flip-flop next. Let's go ahead and make a symbol out of this. File, create, update. So before we stop, create, update, create symbol files for current file. All right, I'll put that in my project folder, my block symbol file. Okay, I could make a new schematic then, file. And I could insert this in here, so insert the symbol. And it's up in my project folder. There it is. All right, when I use that symbol, that represents my solution. So out here, I can make a hardware level, right, where I start using maybe switch 0 as an input X, and use a push button for the clock. And so make that bigger. So I could use switch 0. My X, maybe key 0. We'll use a manual clock. Eventually we'll use the board's clock to drive the circuit, but a manual clock lets us make the transitions when we're ready. And all right, let's turn off the text tool. I could then wire. My clock in here. All right, I could use some LEDs. Here and here. Now if I so output Q0 on green LED 0, and output Q1 on green LED 1, we should see our binary state values. Right, X will be driven by switch 0, so that could be a 0 or 1, and clock will be driven by our push buttons. And so I can save that, right, as the name of my project, sequence 110 BDF. This could be my top level block. Now what I might want to do is I don't have a reset signal in here. So I don't necessarily know what state this will start in. Let's go ahead and add the reset to our D flip-flop. Right. Let's go ahead and wire in another input. Call this reset. And so reset gets wired in here. Now with these D flip-flops, I normally don't have to wire the reset and the preset. Hoping Fortis will let me get by with just wiring one and not both. All right, so I added an additional pin here. I need to go ahead and save this. I need to update my file, or my block symbol, create update, create symbol files from current file. Save that, yes, replace the old one. Go back to my top level. If I right click on here now, right, I can say update symbol or block, update this one, and now I've got my extra input, which I'm actually then going to use. Say key 1 is my reset input. So push button 1 is key 1. Right. I've got that top level. I need to import my pin assignments. Actually, I need to decide which board I'm going to use. So we'll do that in the next video. I will stop it here and we will see this run in the next video.